What do you want to do? What do you want to do? We start.
स्ट्रीम है स्ट्रीम चालू है
Guys, the stream has started. You can join it. Live ही है वो live. It's live. Yes.
मिक्स फॉर इंस्टाग्राम पेज
स्पीकर का वही सीन है स्पीकर मेज ऑफ टाइम चल रहा है स्पीकर
Hello sir. Hello sir. Hello. Hello.
इनपुट म्यूट कर दो
Okay sir.
स्ट्रीम पे ना सबका आइडिया
तुम्हारा जो इनपुट है कॉल यहाँ पे
ये तो स्पीच है भी नहीं अबे सॉन्ग में एक सेकंड सॉन्ग में दो से प्रॉब्लम है
कोई तो म्यूटेड है दो इसलिए मैं बोला जो भी म्यूटेड है तू अनम्यूटेड है तू
मैं म्यूटेड हूँ
कोई तो नहीं है अभी हो गए म्यूट
मैं तो म्यूट हूँ मैं तो वही देखने आया कि मैं तो
Why? Because that's how long it takes light to travel from that.
वो मेरे को तो सही आ रहा है
Now, a nanosecond
लेकिन मेरा मीट है वहाँ पे सही आ रहा है
so that transmission delay is but if we look at objects that are farther away, the effect is more pronounced. For example, if we had a magic switch that could turn off the sun, if we flip that switch, it would be 500 seconds before we saw anything happen. Why? Because it takes light 500 seconds to travel from the sun to the earth. So we're not seeing it as it is. We're seeing it as it was 500 seconds ago. Look at the nearest star. We're seeing it as it was 4 years ago. And when we look at the closest galaxy, we're seeing it as it was 25,000 years ago. There is quite a bit of noise on the line. Maybe people could mute their mics. Was conceived in the 1990s to connect the dots, if you will, between this famous image taken by NASA's satellite, launched in 1989. And this is a picture of the oldest flight in the universe. Blobs are temperature homogenators that are the seeds of which galaxies will eventually form. Now, around the same time, the Hubble Space Telescope was launched, and it took the deepest image that it
वो लाइट है ये रख के आ जाता है
and that shows us what the universe looks like. The universe was about 1 billion years old. Hope shows us what the universe was like 100,000 years old. And we see between the evidence seen by Kobe And the epoch that was seen by HST, the Hubble Space Telescope, was mysterious, studied epoch known as the cosmic dark zone. And the dark zone is of great scientific interest because it is the period in the evolution of the universe when the first stars and galaxies were born. Why is it important to study? Because we haven't had right time space to study it, and that was the original motivation for the Webb Space Telescope project. Now, space is expanding. Space is expanding. This analogy tries to explain. Here you have a loaf of raisin that's been set out. You are seated on one even though you're not at the center. You chose to sit on. You see exactly the same thing. When we say space is expanding, we mean that the galaxies are flying through space as if it was a result of some explosion, but rather space itself, space between the galaxies are expanding. So what does this have to do with the Webb Space Telescope? Well, first look at those primeval galaxies in the dark zone. They emit their light in ultraviolet. But as that light travels towards the expanding space, that expanding rays of window is stretched from the very short wavelength ultraviolet to the much longer wavelength infrared. So to see that light today, we have to observe in the infrared part of the spectrum, and we have to build an infrared telescope. So what do we mean by infrared? Light comes to us in an infinite spectrum of wavelengths, from short to infinitely long. Now, everything that we know about the universe around us, all the information comes to us in coded. And what modern astronomers do, modern astronomers, is to extract physics information out of light to learn about the sources that are emitting light. Now, to get all the information, we as astronomers want light. But all light is not so this is why telescopes are in space. Our eyes are a small portion of this electromagnetic spectrum. The part that our eye is sensitive to, so-called visible spectrum, matches a transparent window in the Earth's atmosphere. So our eyes have evolved sensitive to this narrow range of light, denoted by the familiar colors of the rainbow. But there's a lot more light to be had. Short of violet short violet part have yes. Yes, I can hear you. Yes, I can hear you. I suppose.
Hello, hello, hello.
No, sir, I don't want to
Hello.
someone to place and then I send right?
Okay.
Hello, sir.
Yes.
Can we reschedule like after 1 hour because that's time? Then you can join in again.
It would be better if you could be scheduled for another day. Yes, I'm not available. Go on. Say again.
Give me a moment and I'll speak.
Okay.
So you can continue. But the show is the main will end it with we can wrap it up and like that. But you should have
I'm sorry, I didn't understand.
the issue is
Like both sides, you will so that's why all the points of the rules come.
This is on you.
minutes then
Okay, we can wait. Okay, we can.
yeah, we can continue. Sir?
Yes, you want me to go on?
Yes, sir.
So now we start.
Short our eyes cannot see ultraviolet light, but our skin can be burned by it if one stays in the future. Forward of the red part of the spectrum, eyes can see, is the infrared part of the spectrum. Our eyes cannot see infrared light, but our skin can sense it. If you hold your hand near a warm stove or on your skin,
Gar,
what's
वहाँ से लैपटॉप लेना. घर 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 वहाँ से लैपटॉप. यहाँ टीवी के ये साइड से. इधर आना. भाई एक स्पीकर नहीं ला. केबल लग जाए. और इधर से स्पीकर पे लगाना शायद.
Now, the spaces between the stars, so-called
इसका माइक खराब. वो जो नॉर्मल गूगल वाला ये अरे
this picture taken by the Space Telescope is a giant white cloud formed of stars on this cloud of molecular hydrogen, and that is causing molecules to break up and emit this visible negative as atomic Now, the Webb Hubble Space Telescope zoomed in on a portion of this whole nebula to take this famous image called the submarine. So what we have here are filaments of a giant cloud of molecular hydrogen. And those filaments look brown and opaque because the gas is mixed with dust. The optical light cannot see through that dust. But these are the birthplaces of stars inside these molecular hydrogen clouds. Now, when we look at the same object, infrared, with Webb Space Telescope, the longer wave
Yeah, I think it's clear now. YouTube वाला लिंक डाल देंगे ग्रुप्स पे
Here's another example of a different molecular cloud that's like stars. Here you see hydrogen gas streaming off into space as the emission from the warm stars is breaking up into the cloud. One can see shock and lots of star formation. Some of the objects here that don't have frantic lights are warm stars that are still embedded in their nascent gas cloud. Alright, we know the basics of how stars giant clouds of gas in space respond to themselves by self-gravity. And when this happens, the pressure inside the cloud begins to rise. And when the pressure begins to rise, the temperature also begins to rise. It's much like when you fill your bicycle tire compressed air with the tire is fully compressed, it gets warm. In the first of these clouds, it gets really warm to the point where nuclear fusion can occur, and then the star is born. When this happens, there's typically a giant outflow jet that occurs at the poles of the star, and then there is a disk of material, a so-called circumstellar disk that surrounds the new star. That disk has material left over from the star formation. And these circumstellar disks are of tremendous scientific interest because they are birthplaces of planetary systems like our own. When planets form in this disk, they have to take on sculpted bullseye of radio telescope imagery, sculpted circumstellar disks. One can see that by observing the shapes of homologies of these disks, we can infer the presence of exoplanets without even seeing the exoplanets themselves. And the Webb telescope is doing a great deal of work on circumstellar disks and information. One of the most studied circumstellar disks is that around the star. Data on Omaha. In the center, we have a picture of Omaha taken with the infrared mission that came through the Webb, the Spitzer Space Telescope. And what we saw was this sort of fuzzy blob that was filled with infrared emission. But with the Webb's ability to see the actual structure of this disk. We can see it much more clearly than even the Hubble Space Telescope was able to show us. Much of the science that comes from the Webb comes from its ability to see fine detail in the infrared. Here we see another example. If you look closely at this image, you can see this dark line here. That is a circumstellar disk seen edge on. And here you can see the big bipolar outflow jets. This is another example. It's doing using its ability to see detail to do a lot of work on circumstances in an effort to understand how planets form and how the planetary systems there are out there and how they compare to our own. The closest star forming region to the Earth is Rho Vitae. It's about 400 light years away, and it contains the web image of Rho. And it contains about 50 stars that are similar in mass to our star, the Sun. This is one of them right here, and you can see that the radiation from the stars comes down through this giant cavity in this molecular cloud. All right. Here in the upper left, we have the largest biggest around our star, Sun. Alongside of that, of where that debris actually exists. These are so-called trans-Newtonian objects or Kuiper belt objects. These are chunks of rock and ice left over from the formation of our solar system. And so as you can imagine, we really want to study these primordial chunks of material that our solar system. So we put special concepts and tracking capabilities into the Webb telescope to allow us to observe these objects at the outer planets of our solar system. Now, recently we got our very first image of a Kuiper belt object taken by NASA by mission. And when it finished part of its mission, we sent it on to image this Kuiper belt object for the first time in this so it turned out to be two objects.
फाइनेंस का है सोफी को भेजा है
अलग ऑडिशन
और फाइनेंस के लिए लोग पागल हैं सोफी का है तेरे पास
between these two objects, it has been shown that objects that fuse under those conditions without either one being destroyed. This is very important for the theory of planet formation in which planets form from successive conglomeration of smaller particles into larger ones. Most of the liquid water in our solar system on the Earth, moons of Jupiter and moons of Saturn are believed to have vast oceans that are covered by a thick crust of ice. And when tidal forces act on that ice cracks, and it results in a geyser-like phenomenon where the material from this underlying ocean is ejected from the ice into space. Here's an actual image of that taking place on this moon of Saturn. This was taken with the sea. This phenomenon is very search for life.
कॉल एंड हो गई स्क्रीन इस लैपटॉप से कर रहे हैं स्ट्रीमिंग इस लैपटॉप से हो रही है उस लैपटॉप से हो रही है
स्ट्रीम उसमें हो रहा है उसमें नहीं
क्योंकि यूट्यूब पे
6 months. So every 6 months, the Webb can observe any spot in the sky and still be its sun shield. Now, we didn't have exactly at the L2 point. We put it in a small orbit about the L2 point, as shown here. Why did we do that? We did that to keep the Webb. We're generating electricity on the Webb. It takes about 2 kilowatts of power to run the Webb. And so it's important that the Webb be out of the Earth's shadow. Another feature of the L2 point that is ideal for the Webb mission is that one can see that the range between the distance Earth remains constant no matter how long the mission lasts. And so this telecommunications range, its constancy, is important for our ability to get the data back, which we do by radio transmission. All right, now the JWST's sunshade was one of the most difficult parts of the mission to realize. The sunshade has 5 layers and it has an SPF of more than 1 million. So if you had this sunshade on the beach, you would be very well protected. It measures about 70 by 40 feet, so it is literally the size of a tennis court. It requires 5 layers to get that SPF of more than 1 million. Each layer is made of a plastic-like material called Kapton, and each layer is thinner than a human hair. The sun-facing side is coated with silicon, so it actually looks pink in reality. And the rest of the surfaces are coated with aluminum. The sunshade has a very specific curved shape to give it that thermal performance. And those of you who sew may realize that to make something curved out of flat cloth, it requires lots and lots of seams. And each of these layers is itself a quilt of 50 pieces involving 7,000 inches of seaming. Here it's not done with needle and thread, but with thermal spot welds. The technology of this sun shield, building it, testing it, and figuring out how to deploy it on orbit was really the most challenging part of the Webb mission. Here's an example of just some testing that we were doing on this sun shield. Here, the sun shield is folded up in a containment pallet, and these telescoping booms are pulling it out of the pallet just the way it happens on space. These Mylar tables are there for gravity offloading in this test. They aren't there in space. You can see a person appearing in the center here that gives you a sense of scale. This thing is truly enormous. And after it's pulled out of the pallet, these spreader bar assemblies tension a cord that runs around the periphery of each layer, causing it to take on its specific shape. You get the idea. All right, the sun shield, as I mentioned, was very 140 release mechanisms. Animation that you see here, 7 assemblies, 400 pulleys, controlling as 400 meters of cabling. This was a very high risk, very complex deployment, but it did work perfectly, and the Webb is in great shape in terms of its thermal performance. All right, how did we solve the problem of the mirror being bigger in diameter than the big rocket? Well, instead of building a single 6.5 meter mirror, we adopted something called a segmented mirror architecture, in which we built 18 hexagonal segments that are mechanized to play together as if they were segments of a single mirror. And this allows us to fold the telescope up inside the rocket fairing or nose cone. The Webb was launched on a French rocket called the Ariane 5, which has a 5-meter diameter. Launched from Kourou Launch Anna, which is on the east coast of South America. The payload at launch is about 6.5 metric tons, and the origami of unfolding this involved about 50 major deployments and 178 release mechanisms. Every one of those were a single point of potential failure. All right, the Webb telescope mirrors are made of beryllium. Why did we do that? Most telescope mirrors are made of glass, but we chose to make the Webb mirrors out of a metal called beryllium. So points at various objects on it's in the shadow of its sun shield, there will be small thermal gradients that form in the mirror. And we didn't want those thermal gradients to spoil the shape of the mirror. So we had to find material that had a low coefficient of thermal expansion at this enormously low operating temperature of about 50 degrees above absolute zero. And beryllium has that property. The beryllium starts out in a powder form, and we press it under tremendous heat and pressure to form a solid called a billet. And then after we go through all the trouble to do that, we machine away almost all the beryllium. So this is the back side of a flight mirror segment. And this is the front side where you're seeing laboratory equipment reflected in the mirror. What we're trying to do here is make the mirrors as light as possible. When one builds something to fly, regardless of whether it's an aircraft or a spacecraft, weight is a major driver on the engineering design. Here, the figure of merit is mass per unit area. And by that measure, the Webb mirrors are about 6 times lighter than the Hubble Space Telescope mirror. All right. Now, how do we polish telescope mirrors? Well, we rub on them with gritty stuff until they get smooth and shiny enough. That's a room temperature operation. So if we're going to polish the mirrors at room temperature and use them at minus 230 degrees Celsius, it means that we have to put in the wrong shape at room temperature to get the right shape at the operating temperature. This is done through the magic of computer modeling, but computer modeling is not perfect. And so we had to follow an iterative process in which we would polish the mirrors part way and then put them into a specially instrumented space simulation chamber at Marshall Space Flight Center in Huntsville, Alabama, where we could cool the mirrors down to their operating temperature, observe them with special optics test equipment to see how our polishing, how the reality was tracking to the model. Then we would make iterations in the model as necessary and go around this loop. This is one of the reasons why it took so long to build the Webb telescope, but in the end, it was very, very successful. And this is actual flight data here shown in the upper right. So here you have a mirror segment, and these colors denote topographic relief and valleys. And one can see that when we cool that segment down to its operating temperature, the whole thing flattens out to a nearly perfect. And we had to do this for all of the mirror segments. When we finished making the mirrors and populating them onto the telescope structure and integrating all the science instruments to the telescope, we then had something that was too big for aircraft. And so we put it into, shown here, a storage container that maintains the Webb in the super special environment that it has to be in to remain qualified to fly in space. and we shipped out of Steel Beach, California, just south of Los Angeles, on a roll-on, roll-off transport ship. And we went through the Panama Canal to French Guiana. NASA has ever delivered a payload by boat. That all went very, very well. All right, here we are in French Guiana, and we are riding up an elevator alongside the Ariane 5 rocket. There are work platforms set up alongside the rocket where people are getting the rocket ready to fly. We're going to the top to see where the Webb telescope is being joined to the rocket. This is the last view of the Webb telescope on Earth. The spacecraft is fully fueled at this point, so you can see that the technicians are wearing these special safety suits to protect them from any fuel leak. And they're bolting the Webb onto the rocket and then putting on the fairing or nose cone. And then the rocket is rolled out of this assembly building to the launch site. It really moves very slowly. You can walk alongside it. And then we launched it.
Decollage liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Okay, the launch went very well. And these are the deployments that occur right after launch. First, you saw the solar array come out so that we could become power positive. We're operating on batteries up to that point. And the high gain antenna came out so that we could begin talking to the Webb as it travels out to the L2 point and unfolds itself. We followed what's called a direct transfer trajectory to get to the L2 point. We didn't orbit the Earth even once, and we got an extremely precise launch from Ariane space. This is how the telescope unfolds. You saw the primary mirror structure unfold, and here things of the primary mirror unfold much like a round drop leaf kitchen table. All right, now when we first get the Webb on orbit and we first point it to a star, we have 18 separate telescopes. We have 18 segments that need to be aligned. Mechanized in 7 degrees of freedom, 6 that you're familiar with, plus radius of curvature. And so we point the telescope at a star, and we get 18 images of that star. Then we would move each segment to figure out which image went with which segment. And then we superimpose all the images onto each other. And then we use special interferometric optics in one of our science instruments to make each segment coplanar to its neighbors to within a small fraction of the wavelength of light being observed. And then we have a nearly perfect image. And the Webb is exceeding its image quality requirements by about a factor of 2. Webb is giving humanity its very first high-definition view of the infrared universe. And this chart shows what we mean by that. Our first infrared mission of recent times, mission, 2009 to 2011, WISE was a very small telescope, just 40 centimeters in diameter. And this is the clarity that one can get with that small telescope at these long wavelengths. WISE was followed by the Spitzer telescope. So here we're observing the exact same field of in the with Spitzer, and we see it's a little more. And then the Webb, with its 6.5 meter diameter mirror, gives us this stunning clarity, similar to the clarity that the Hubble Space Telescope, gives us in the optical. The magic here is just given by this simple The bigger the mirror diameter, the smaller the resolution element, the smaller the smallest feature is that we can see. Here is an example of Webb giving us incredible clarity on nearby galaxies with its remarkable spatial resolution. We have never had this kind of clarity in the infrared before. We're able to obtain spectra of those galaxies, just as we do with the exoplanet atmospheres, and we are able to measure the chemistry of galaxies that are just a few hundred million years after the Big Bang in their form shift galaxies. We're able to measure the shape the universe was less than 1 billion years old. And this was a big surprise. We expected these galaxies to all have irregular shapes or irregular morphologies, but that's not necessarily true. Some of these very high redshift galaxies have disks and spiral arms. Some are elongated. So this is one surprise that the Webb is giving us. Yes?
10 minutes because we have to end this call.
Yes.
Okay, thank you.
Webb has seen, by working with the Chandra Space Telescope, a new type of black hole. The black holes were typically these black holes were theoretically predicted to result from a collapse of massive clouds in the interstellar medium. And this may be a first observational example of that. The Webb has seen dwarf galaxies reionizing the universe. The universe, shortly after the epoch seen by Kobe, was neutral. And as these galaxies put out lots of ultraviolet radiation, they ionize a bubble around themselves. And as those bubbles to form the ionized interstellar medium that we have today, and the Webb has observed this process. When a star that is the mass of our sun runs out of fuel, it will shed its atmosphere to produce an called a planetary nebula. And the Webb this is a Webb image of a very famous one showing the remarkable detail in these objects that we have never seen before. When a star much more massive than our sun runs out of fuel, it produces a much bigger explosion called a supernova, and it leaves behind a remnant called a supernova remnant. And this is a picture of a famous one called Cassiopeia A that occurred 340 years ago, so within recorded history. These supernova are very, very interesting objects. This is where all of the heavy elements in the periodic table are forged. And so the calcium in our bones, the iron in our blood, the gold and silver in our jewelry was all made in the supernova explosions like this. The Webb had, in the most recent supernova to occur near us, supernova 1987A, the Webb has imaged its remnant, and we can actually see the progenitor star in the Webb images for the first time. So how does the universe work? How did we get here? Where are we going? And are we alone? The Webb mission enables the next step in humanity's quest for the answers to these questions, and you can join that quest. The people that use and build space observatories come from all walks of life and all backgrounds. There's a quote that I like to read. The book of nature lies continuously open before our eyes, but it cannot be understood without first learning to understand the language and characters in which it is written. It is written in mathematical language, and its characters are geometrical figures. That's as true today as it was 400 years ago when Galileo said it. So if you would like to work on projects like this, go to college, or if you're already in college, stay there, study whatever you love. But if that happens to include science, engineering, and math, consider this as a career objective. And if you would like to explore doing science by joining an actual science team, NASA has a program to do that called Citizen Science. The website is here, and you don't need to be a U.S. citizen to participate in that. And you can join with a real research team and help do the research and understand what it's like. So that's the end of our presentation today. What's coming up in a few months in October, the Europa Clipper satellite will travel out to one of those ocean worlds we talked about to work on the search for life. In 2025, the Sphere X Observatory will be launched. That will take an infrared spectrum of every spot in the whole sky. In 2027, the Roman Space Telescope will launch to study the phenomena of dark energy, which is causing the expansion of the universe to accelerate. Then in 2028, the Dragonfly mission, which is a helicopter, will be sent to explore the surface of Titan. And then in 2040, the Habitable Worlds Observer will be launched to study Earth-like exoplanets around sun-like stars. All right, so those are my remarks for this afternoon. Sorry about all the technical difficulties, and back to the host.
Hello, sir.
Yes.
Uh, we'll take some questions and
Yes.
then we can answer. First, we'll take some questions of the students, right, sir?
Yes, that's fine.
Did the findings of James Webb Space Telescope challenge any of our known laws of physics?
Could you repeat the question?
Yes. So I was asking if the findings of the James Webb Space Telescope challenge any of our existing laws of physics, and how did we overcome that?
Okay. So the question is the Webb challenging our knowledge of physics? It has not yet, broken physics. It's giving us lots. It's definitely challenging our prior ideas about how galaxies form and evolve and how long the process of galaxy evolution takes. But the solutions to that don't require any new physics at yet.
What kind of technical advancements do you expect in telescopes in the coming decades?
Well, boy, there's a lot there. The Habitable Worlds Observer, which is the next big telescope that we're starting to work on, it will operate at much shorter wavelengths, necessitates some optics challenges, and it will have stability and to observe exoplanets. And so that will be a particular challenge that we will have to. And detectors are always sort of a cutting edge technology. We are always flying, the most advanced detectors that exist. And so the next observatories that I mentioned that will be flying will have detectors that are even more advanced than those on the Webb telescope.
sir.
Yes.
So it was nice having you here. I'm so sorry for the trouble that we caused in the starting, but it was very interesting talk. Our audience enjoyed it, like they really enjoyed it, and they were. But now,
Okay, great. Thank you for having me.
thank you, sir. Thank you so much.